Okay, so we're talking about the comparing population means. We're talking about comparing population means. And we're going to do hypothesis testing and confidence intervals for comparing means. So if we don't have, just like before, if we don't have the sigmas and we only have the sample standard deviation, the standard deviation of the samples, we're going to use the t-test. And then the other quality here, the other fact that we have is we're going to assume, so that's number one. That's the first thing about our test. Number two is the standard deviations are not assumed to be equal. Okay, and this is then what we call, we're going to use an unpooled test. That's going to be important when we're using MyStatLab, that we choose that to unpooled. And so we use unpooled when standard deviations are assumed to be not equal. So the only place that comes into play is when you're using MyStatLab, you're going to make sure you uncheck the box that says pooled results or something like that. I mean, we'll see that in a second. Okay, so these are the problems that we're going to do, okay? So let me just show you. Do not copy this next thing down. I'm just going to show you. Okay, so our assumptions, we have simple random samples, they're independent, and the populations are normal, or we have large samples, so that we have a normal distribution. Okay, so again, we said the two-tailed test, we're saying the alternative hypothesis is that your population means are not equal. The left-tailed test is that your first population mean is less than the second population mean. Right-tailed, first population mean greater than the second population mean. Okay, we're going to have a significance level. And then here is our test statistic. So what was it before? T before was?
X bar minus U X bar.
Right.
Over, divided by S over the square root of n.
So this was for just the old hypothesis test that we were doing just for one population. So notice that it's similar, right? So we're going to take the difference. We're going to take the difference of our sample means, and then we have a similar kind of formula down here where it involves the sample standard deviations and the sizes with square root, right? So that you see this is kind of similar. But we're not going to do that. We're going to use MyStatLab to do all this work for us, okay? But just notice the similarity, right, between what we had for one population and one sample, and then two populations and one sample from each of two populations. Similar type formula. Okay, and then since it's a t-test, we also need what to use our table? Remember what else we need in the t-test? Degrees of freedom. So that's the really ugly one here. So for our t-test, so here's why we're using MyStatLab mostly. It's because here's the degrees of freedom formula. Okay, it's really complicated as opposed to what? One less than your sample size. So you see that in there, but that's only a small part of a very complicated formula. So this is the degrees of freedom for this comparison test of two different populations. But here's the key fact. When we get that degrees of freedom, that will be a decimal, could be a decimal value, and then to use the table, we're going to round down, always round down to the nearest integer. So even if it's 21.9, if your degrees of freedom is 21.9, what are you going to look in the table? 21. You're not going to do 22. You're going to look at 21. Okay. So we're still going to use the same t-table, but we'll have our degrees of freedom will be a decimal. We want to just truncate it, just chop off the decimal and take the lowest integer for the table. Okay, and then our picture looks the same, right? Two-tailed. We'll have the rejection region will be out on the wings here, and then the left-tailed will just be the rejection region will be on the left side. Right-tailed rejection region on the right side. Okay, if the value of the test statistics falls in the rejection region, reject H0, otherwise do not reject H0. Same types of conclusions as before, but now it's about comparing. It's about comparing two population means versus just what is the population mean. So before it was like we were looking at, is the population mean, say, greater than a certain value or less than a certain value? Now it's comparing two population means. Okay, so let's see if we can find an example here. Oh, so this is now confidence interval. So confidence interval, again, is to say that we are a certain amount confident that the difference between the means is a certain value, right? So this should look familiar. So instead of it just being just looking at one sample and one population, now we're looking at the difference between the two. And so it's going to be the difference plus or minus t times, so this is a number of standard deviations times the standard deviation of our combined results. Okay, so this is also the same, but my stat lab is going to be doing the heavy duty calculating for us. But so because of that, it's all the more important that we are interpreting results and understanding it correctly, right? We're letting the technology do the ugly stuff, but then so that it's up to us to be good managers of the information, right? So that's not enough. We have to still understand what's going on. Okay, so that's not us. So let's do some examples here. So in the book, that's worse. Okay, so we'll just do our best here. So let's do 1076. So write down that information for 1076. So what is x bar 1? What is x bar 1? Yeah, what does it mean now? So what are we talking about when we say x bar 1 equals 15? What is that? Yep, so we took a sample from population 1 and we took the mean of that sample and we got 15. Okay, what is S1? Sample standard deviation. Okay, again, indicating we're going to use a t-test, right? N1 then is our sample size. So we took 15 observations of population 1. We got a mean of 15 with a standard deviation of 2. Okay, then we had another population. We also took 15, a size of 15, and then we got a mean of 12 and a standard deviation of 5. So when it says we're going to do a two-tailed test with alpha equals 0.05, what is that about? What we say a two-tailed test, alpha equals 0.05. What are we testing? So what are we testing? Sorry. What are we testing with a two-tailed test in this case? What is it that we're? Can you write the null and an alternative hypothesis and interpret those? What is it? What do they mean? Gina, want to try? Do you want to try?
The null hypothesis would be H colon U1 equals U2.
And so what does that mean? So you said so mu1 equals mu2.
The population mean of the population mean of population 1 equals the population mean of population 2.
Right. Our null hypothesis is that the population means, whatever these populations are equal.
For population mean 1 minus population mean 2 equals 0.
Right. Okay. Alternative hypothesis?
Alternative hypothesis would be the population mean of population 1 does not equal the population mean of population 2.
If it's a two-tailed test, then we're just saying, you know, either the alternative is they're not equal. So it could be one is higher than the other, or the reverse. Okay. So we're testing to see if these populations have a different mean or the same mean. Okay. Or if there's enough evidence to suggest. Okay. So we have an alpha of 0.05. And so here's where we're going to use my stat lab to do the work for us. Okay, so questions on what it is we're testing. So if I could try to make this into an example here. So let's say I don't know. So you had two. This is not a great example, but you have two typing classes. Okay, two typing classes, and we took 15 students, and we from the first typing class, and we got their words per minute, and their average words per minute of those 15 sample in the first class was 15 words per minute. Okay, it's really slow, but I think still serves a purpose. And then the second typing class, we took 15 students from the second typing class, and we had them type, and their average words per minute typing was 12 words per minute. So now we're asking, is one class faster than the other at typing, or not? Or is there enough evidence to say that one class are faster typers than the other class? Does that make sense? So that's kind of that's just trying to put some real world context to what we're doing here. So we don't care that the first class is faster or slower. We're just asking, are they different? Or is there not enough evidence to suggest that these classes are typing on the average at different speeds? Okay, so I'll show you how we do this here. My stat lab. Or sorry, Statcrunch. I don't know what I've been saying, but Statcrunch is what I've been talking about when I've been saying let's have the technology do it for us. So in let's see here. So if you're at the main menu, so you're not going to have in these problems, I don't think you're going to have a direct link to Statcrunch like we've had in the past. So I'm going to show you this. It's at the main. So if you go to the main menu here, it's just part of your main menu, and then when you go to the course in my stat lab. So yeah, so over here in the left-hand menu, you should have a thing that says Statcrunch. If you click on that, it should open it. And then open Statcrunch. Okay, and you can even go, so you can even just use it, you know how there's links to certain problems. If you can just find a place where you can link to it and just click on it, it'll give you the data for that problem, but it doesn't matter. You can just ignore that and still use it. Okay, so you can still use this, I can still use this window to do our problem. Okay, so here's what we're going to do. We're going to go to stat, and we're going to go to T-stats, and we're doing to sample now. And so with data would mean that we're going to enter in the actual individual data values of the sample. With summary, that's what we were given. So that in our problem, we have the summary. We have the sample mean, sample standard deviation, size of the sample. So I'll show this again one more time. Stat, T-stats, to sample for this problem with summary. Okay, so what was our sample mean number 1? 15? Sample standard deviation was 2, 15, then 12, 5, 15. Okay, so here's this thing, calculation options. We want unpooled, so all the problems we will do will be unpooled, and that means we're assuming that the population standard deviations are different. So we're always gonna uncheck that box when we do these. Okay. So our hypothesis test is we're going to say that the null hypothesis is always going to be that the population means are equal. So this will always be 0. Okay, and then you have the choice of the alternative hypothesis. Mu1 being not equal, less than, or greater. So two-tailed test means not equal. We'll just leave it at not equal. This is for a confidence interval. We're not doing a confidence interval, so you just leave this blank. Okay, don't do it. You're not checking that. We're just looking at the hypothesis test. So we got all that. We put in the summary stats, and we've got the two-tailed test, and we hit compute. Okay, and so then it gives us here's what we're going to need, right? Degrees of freedom. What are we going to use? It's 18.368. So we will use 18. Always round down. Okay? Our T-stat, we're going to use that. This is going to be this is our test statistic, 2.15.
You'd even round down with the T-stat?
No. Just get enough decimal places. So say 2.158. It's good. 3 decimal places is fine.
Okay.
P-value is 0.044. We can get away without that, but we remember what that is. That's the area under the curve that we're comparing to alpha, right? Or the probability, what? Probability of making a type 1 error. Okay, so this is our test statistic, and we got our degrees of freedom. So what do we need? We need the critical value. How are we going to get the critical value to compare with the 2.158, our test statistic? How are we going to get the critical value? Same way we did before.
Yeah.
Okay, what's our significance level? 0.05, and if it's a two-tailed test,
0.025.
right, for a two-tailed test, we're going to 0.025. Because we're going to use alpha over 2. So how do we get T of alpha over 2? It's 18 degrees of freedom and a alpha over 2 of 0.025. Where's that critical value going to come from? A few of you are shuffling through your papers. That's right. Where are you looking? Okay, so here's 0. You got what? So 18 degrees of freedom for your T of 0.025. 2.101? 2.101, okay? So, but that's going to be plus or minus, right? So our critical value is going to be 2.101 and negative 2.101. So then where's our rejection region? Our rejection region is out here to the right, and then out here to the left is all rejection. And what was our test statistic? What did we get? 2.158. And so does that fall in the non-rejection region or the rejection region? Rejection region. So there's the 2 point. .158. Okay, so what's our conclusion in the test? Reject the null hypothesis. So we're going to reject H naught, and then how do we interpret that? Or why are we rejecting? Is there evidence or is there not enough evidence? There is evidence to suggest.
Population mean of population 1 is not equal to the population mean of population 2.
Right. There is evidence to suggest that the population means are different, or that population mean 1 is different than population mean 2. At the 5% significance level. Okay? So what does that mean? It means that there's evidence to suggest that these two classes don't type at the same average speed, right? That these two classes type at different speeds. Okay, anybody have a question? So yes, we're using my stat lab to do the heavy lifting for us in terms of the computing, but we still have to know what's going on, right? We still have to know how to get the here, sir. What's your name and date? Piece of paper. There's lots of things we had to manage and understand. So yes, we're using the Statcrunch to help us, but there's a lot of management issues and interpretation issues that we still have to attend to. So let's try another example with a real world situation here. So let's try. There we go, perfect. All right, so this is about sizes of tumors, malignant versus benign tumors. Okay, and so there's this hypothesis that that malignant tumors are larger than benign tumors. So what is this in millimeters? So this is the size of tumors in millimeters. Size of tumors in millimeters, and the standard deviations, and then the sample size of, this is 52 malignant tumors, 116 benign tumors. So the sample mean of the malignant tumors is 48.5 millimeters, benign 33.7. So is there enough evidence to suggest that malignant tumors are bigger? Malignant tumors are bigger than benign tumors. That's what we're going to check, and we're going to check that at the 1% significance level, meaning we only want to make a type 1 error. We want to incorrectly reject only 1% of the time. Okay? All right, so let's do this one together, and then we'll have you do one for the sheet. Okay? So where are we going to start? We're going to start with our null and alternative hypotheses. So, Daisy, what's the null hypothesis? That's right. Or in other words, the null hypothesis is that malignant tumors and benign tumors are the same on the average. So on the average, all malignant and benign tumors are the same size. Okay? Alternate hypothesis in this case would be, Madison.
That the first mu for the malignant is going to be bigger than the...
That's right. And so that's also like saying that mu1 minus mu2 is what? So is this a right-tailed test or a left-tailed test? Right-tailed test. Right-tailed test. Okay, so we're ready to go. We got our data. Did you guys write down the table numbers? Because I'm going to go to Statcrunch. So again, any way you can get to Statcrunch, you can get to it from an example like this, or you can just go to my stat lab and use the left-hand menu. But any way you can open up you can even have data in it. Doesn't matter. Okay. So we're going to again stat, Tstats, to sample. Again, we have the summary. So you might have a problem where you have data. So instead, it'll give you the actual observations instead of the mean, standard deviation, etc. But we're given the summary in this problem. And here we go. So this is malignant tumors. Sample mean is? What was it?
48.5.
Thank you.
38.5.
What was the sample standard deviation for malignant tumors?
38.5.
Oh, wow. Huge. Okay, so big variability. All right.
52.
I thought you were giving me another mean, right? So that means that the size of these 52 malignant tumors had a really wide spread of values, right? They weren't all close to 48.5. It's a huge standard deviation. Okay, sample mean number 2.
33.7.
Okay.
26.6. 116.
Did I get that right? Okay, cool. And then we make sure you're not pooling variances. And then, what is our hypothesis test? Yeah, so we want the alternative now to be a right-tail test, such so that population mean 1 is greater than population mean 2, so that the difference is greater than 0. Okay, we're ready to go. Compute it. We're going to get our... Okay, so I've got degrees of freedom, 73.66. So what are we going to use for the table?
73.
Use 73 degrees of freedom. Our T-stat, 2.516. Okay, so for 73 degrees of freedom, and then what is our T, what is our alpha? 0.01. Are we going to divide by 2?
No.
No, it's a right-tail test, so we're just going to go to 0.01. And what is T for 0.01 with 73 degrees of freedom? Is that on your table?
No, 70, but 2.381.
Is there 70 on the table? 70
70.
is what? What is it?
2.381.
And what was 69? What is it if you go up?
It's 60.
So 60 is what?
2.390.
So 60 is 2.39, 70 is 2.3.
2.381.
Okay, so tell me what for 60 it was again?
60 is 2.390.
Okay, so it's not gonna. Yeah. So 60 was 2.39, and 70 is 2.38. Then 73 is going to be 2.38 or maybe 2.37. Okay, but it's not. It's not going to. They're getting less anyway, right? So as you go up, they're getting less, and we're comparing it to 2.516. So we're okay to just use the 70 instead of 73. It's not going to make a difference for our conclusion. Okay, so here we go. So we are doing a right-tailed test this time. So what is our critical value? Did you got that? We got that as 2.838 basically. And then, so there's our rejection region. And then what is our test statistic? 2.516, which is up here. Conclusion? Reject the null.
Reject the null.
Because there is or not sufficient evidence. There is evidence to suggest what about the tumors? That's right. There is evidence at 1% significance level that malignant tumors are bigger. Okay, any questions? Does it make sense?
What is the 1% significance level? Like, will that change? Or is that
So that means that this area is 1%, and it means there's a 1% chance that we made a type 1 error. Remember that? So it's 1%. There's a 1% chance that the data we got was such that we rejected, but we shouldn't have rejected. Okay, so let's have you guys try one. Okay, let's do 1078. Oh, we never did the confidence interval. So let's go back to that last example and look at what a confidence interval would mean. So let's go back before you do a new problem for the sheet. So where were we? So when you're done, so you have this data. So this is helpful. You have the numbers that Statcrunch helped you with. If you go to options and go to edit, it takes you back to this screen where you'd already input where all that information is inputted. Okay. So now we want to let's do a confidence interval on this and see what that means. Okay. So we're gonna put in this summary information, and then we're gonna do instead. Now we're gonna click on confidence interval, and so let's do a 95% confidence interval. If it's 90, you're gonna change it to 0.90. 99, you can change it to 0.99. So we'll just do a 95% confidence interval for the sample data that we got, and if so, we'll compute. And so we got a lower limit of 3.077 and an upper limit of 26.52. So what do those numbers mean? So that's like 3.078 and 26.522. Okay, so what's the center of that?
Be 0.
Nope.
No?
Between 3 and 26.522.
Minus.
And what are the meanings of these numbers, right?
Okay.
So confidence interval for what? Here's the key. What variable are we doing a confidence interval for? What variable? Did you get 14.8? So what do these numbers mean? It's 3.078 what? 14.8 what? 26.522 what? Anybody know? Remember we had two different so we've got two different samples. We got benign tumors, malignant tumors, but we have one variable to investigate if they're different or the same. What's the one variable the one number that can investigate if comparing the two tumor sizes? We're gonna give it a shot.
Sample mean?
But there's two samples. There's a sample mean for.
So the difference.
Was that? Yeah, the variable is the difference, right? The variable is the difference in sample means. So what malignant tumors was? What was the sample mean for malignant tumors? 48 point something.
48.5.
5. That was X bar 1. And what was X bar 2?
33.7.
So if we're comparing and we need one number that helps us compare, well, we'll do the difference. That's 14.8. See? So what? We're 95% confident that what? That the difference in tumor size is between.
Between 3.078 and 26.522.
We're 95% confident that the average difference between malignant and benign tumor size is at least 3.078 and at most 26.522 millimeters. The best we can guess the true difference between them is the difference of our sample means, because that's the data we have. So 14.8 would be our point estimate at how much bigger malignant tumors are than benign tumors. But we're 95% confident that they're at least 3 millimeters bigger and at most 26 millimeters bigger malign tumors than benign tumors. Malignant tumors than benign tumors. So that's important. You can interpret that. So difference of means. And so this very well could have been a negative number, right? Meaning that there's, within the 95% confidence, benign tumors are bigger, right? You get a negative value. But in our 95% confidence interval, we're 95% confident malignant tumors are at least 3 millimeters larger and at most 26.5 millimeters larger. Okay, so now let's do the example. Any questions on the confidence interval? So with confidence interval, all you have to do is use Statcrunch and interpret correctly, know what the numbers mean. So we're going to do 10.78. Write that down. And I'll do the Statcrunch, and then you'll do the rest. Okay, everyone got it? All right, so we'll do the Statcrunch together, and then it's up to you to do the rest on your sheet. Okay, sample mean number 1.
20.
20. Standard deviation?
4.
4. Sample size?
10.
10. Number 2.
23.
23.
5.
5.
And 15.
15. Okay, make sure you uncheck pool variances. We want unpooled results. We're doing a hypothesis test. What will my alternative hypothesis be for a left-tailed test? Not equal, less than, or greater than? Less than. Right? So the difference between mu1 and mu2 is going to be negative if mu1 is less than mu2. That's our left-tailed test. Okay, here are the numbers. So what I want you to do, I want you to write the null and alternative hypothesis, write the hypotheses. So determine the critical value and make a picture of the rejection region. Remember, this is a left-tailed test. So work together, check your answers with each other. But everyone got so you're going to make your right hypotheses, determine the critical value, make a picture sketching the rejection and non-rejection regions, and then make your conclusion and interpret.